A very good place to start learning about surge protection is looking at the cause of transients. The surge magnitude or the amplitude of surge in all cases is driven by the rate of change of fluid velocity. So what are the events that typically create velocity changes in fluid systems? We will start with the obvious events, pumps turning on or off, and pumps can suddenly lose their electric power source. Valves can open and close either by human manual intervention or under automatic control. Velocity changes in a drinking water pipe network can be driven by increases or decreases in customer demand. For example, the morning peak period arrives as everybody in town wakes up and starts their daily activities. Typically, the gross change in customer demand happens slowly. That is, not fast enough to generate significant surge amplitudes. However, sitting behind each increase or decrease in customer demand is a tap, which is just a small valve, or a solenoid valve being turned on or off. Thinking about customer sites which can generate larger flow rates, for example a process plant, a fire protection system, or a landscaped irrigation system, their changes in demand are driven by a pump starting or stopping, or a valve opening or closing. Consequently, your engineering career is likely to include protecting systems from pressure surges created by the operation of pumps and valves. Let us take the next step by looking at a list of possible surge protection methods. The methods can be divided into two groups. Those which aim to directly control the rate of velocity change, the cause of surges, and those which only treat the symptoms. When developing surge protection for a system, you may find it helpful to start looking for solutions which target the cause of surges, the rate of velocity change, rather than solutions that just treat the symptoms of high head or low head. The reason being that controlling the rate of velocity change, the cause of surge, tends to have benefits across the whole system. Treating only the high or low head symptoms tends to only be effective at specific points in the system. If the system configuration changes in the future, more treatments at different locations may be required. Methods which aim to control the rate of velocity change achieve this by the following approaches: diverting and absorbing the kinetic energy available in the moving fluid. For example, when a pump stops or power fails to a whole pumping station. A typical example would be the kinetic energy upstream of a pump station that has a long, large diameter suction main. The diversion of energy extends the period of time taken to bring the fluid to rest. As a result, the rate of velocity change is reduced. Some systems may require lost energy to be replaced. For example, on the delivery side of a pump station after a pump stops or power fails to a whole pumping station. Replacing the energy that is no longer available from the pump motors with energy from another source extends the time taken for the fluid to come to rest, which reduces the rate of velocity change. In some situations, it may be possible to directly control the size of the velocity change in the fluid system. For example, undersized pipes on a system mean higher initial steady-state velocities. Designing the system with larger diameters directly lowers the size of the velocity change that will occur when a pump stops or a valve closes. Methods that control the symptoms of surge include, starting with the obvious one, select the pipe, valve and fitting classes to be strong enough to cope with the maximum surge heads. When project economics can carry the capital cost of the required pressure classes, clients often select this option because it's a passive, always present and reliable solution, and the capital and operating costs associated with additional surge protection assets are avoided. In other words, it's a simple passive solution. The second approach is to install devices which limit the maximum head experienced during a surge event. On some systems, the need can be to install devices which limit the minimum head experienced during a surge event. A common example being drinking water systems where negative heads can introduce the risk of sucking contaminated groundwater into the pipework through leaky joints. The final option is to reshape the system configuration in a way that reshapes the size of the surge problem or changes the location of the problem.